In this video, we're going to do an example of analyzing a circuit where you've got mutual inductance or a magnetic coupling between two devices within the circuit. So in this circuit here, we've got an inductor here, a 500 millihenry inductor here, and a 250 millihenry inductor here. And we're told that there is a magnetic coupling between the two with a coefficient of coupling of 0.45, so K equals 0.45. So first of all, we need to identify what the mutual inductance M is. And of course, M we know to be equal to K times the square root of L1 times L2. So that's going to be 0.45 times the square root of 0.5 times 0.25. And M turns out to equal 0.159 henries. So there's effectively a 0.159 or 159 millihenry cross or mutual inductance between those two devices. Now that we know what M is, we can go through and convert the entire circuit to its sinusoidal steady state because it is being driven by a source that's oscillating at 10,000 radians per second. So Z sub M then is equal to J times omega times M, which will be J times omega, which is 10,000, times N, which is 0.159. We find that Z sub M then is equal to J 1590. We can also find ZL1, that's equal to J times omega times 0.5, and that turns out to be J 5000. And Z for L2 turns out to be equal to J 2500. So let's just go ahead and write those in over here. We've got J 5000 is the impedance of that inductor. J 2500 is the impedance of that inductor. And we have Z sub M. Let's write it Z sub M then is equal to J 1500 and what was it, 90. Over here, this source then will replace in its phasor form as 20 angle 0. And we're now ready to start looking at the circuit. You'll notice that this and these two inductors are, as we've mentioned, coupled. And we've got the dot here, and we've got the dot there. Which is telling us then that there will be, in addition to the self-induction, the voltage across this due to the current through there, through itself, there's also going to be a voltage established that will be due to the current flowing over here. Now the current over here is referenced into the undotted terminal. So the voltage that's going to be induced over here due to this current is going to have a positive sign at the undotted terminal. The current is going into the undotted terminal. The current that's causing this voltage over here is going into the undotted terminal, therefore the voltage will have a positive reference here and minus there, and that's going to be the J 1590 times the current flowing through that coil, which is I2. Now, over here, the voltage that's induced in this coil due to the current in this coil is going to be a little bit tricky because the current in this coil isn't just I1. I1 we're calling this mesh current. I2 we're calling that mesh current. So the current going through this coil is going to be I1 minus I2. And that gives us the current that's entering the coil going from the top down. So the current in this coil, I1 minus I2, is entering the dotted node. Therefore, over on this coil, the voltage that's due to the current in this coil will be referenced positive at the dotted terminal, and we'll have a voltage like that, which is going to equal J 1590 times, I'm learning out of room here, times the current through this coil, which we said was I1, we'll just write it down here, I1 minus I2. With that much preparation, we're now ready to go ahead and write two mesh equations, one around the left loop, one around the right loop. So, KVL left, starting here we'll have a minus 20. Coming on up here through the 1 kilo ohm resistor, we'll have plus 1000 I1 plus, now the current going through here is I2 minus I1. the self-induced voltage will be then J5000 times I1 minus I2. That takes care of the self-induced voltage. Now we have this other voltage over here, which is referenced minus to plus, so it's going to be a minus the voltage we've already determined to be J1590 times I2. Brings us back to where we started, so the sum of those voltages must equal 0. Let's just review these two voltages. This voltage drop here is the voltage due to the induction of this coil, the inductance of this coil, J5000, times the current going through there, which is I1 minus I2. This term right here is the voltage due to current over here, I2, that's coupled through this mutual inductance. So again, that would be, because we're going minus to plus, it would be a minus J1590 I2. Now let's do KVL around the right-hand loop. And over here, let's just start here. We'll have then J500, or J5000, and we're going this way, so it'll be J5000 times the current going this way. The current going that way, of course, is I2 minus I1. Continuing on around there, we've got a plus 2000 I2. Coming on down here, we'll have the self-inductance voltage, which we're going in the direction of I2, so it'll be plus J2500 times I2. So that's just I2, which is the only current in this inductor, times the impedance. Then we also have this mutually induced voltage, which was referenced minus to plus. So as we go across that voltage, we're going minus to plus, so it's going to be a minus. And that voltage was just the mutual impedance, which was J1590, times the current through there, which we found to be current going in this direction, which we saw to be I1 minus I2. And the sum of those terms then must equal 0. With those two equations, we need to just go ahead and combine terms. And I'm going to stop the video here to combine the terms just to save you some time. Alrighty, after combining terms, we then get these two equations, which are all set up to put into a matrix solver of your choice. And when we do that, we have, let's just go ahead and write the A matrix. The A matrix is going to be 1000 plus J5000. And let's put it in parentheses, minus J6590. And then down here we have minus J6590 and 2000 plus J9090 times I1, I2 is equal to 20, 0. So there's our system of equations in matrix form. And when you go through and you solve for that, you get that I1, let me put it up here because I'm running out of room, I1 turns out to equal 0.0098 angle negative 12.47, and I2 equals 0.0069 angle negative 0.066 degrees. Those are both in degrees. Alrighty, so that gives us our two mesh currents. If we wanted to, say for example, determine what the voltage was across that inductor, V out then would just be that inductance, J2500, times the current flowing through there. Well, the current through that inductor is just I2. So times I2, let's just write I2 rather than rewriting it, and you come up with then 17.25 angle 89.94 degrees would be the voltage across that inductor.